Good afternoon, ladies and gentlemen. Thank you for joining us at this Knowledge Sharing Center webinar event again. Good afternoon. Today, we're going to present you a nice subject, an interesting subject, CT scan for industrial parts manufactured by additive manufacturing. And next to me is our guest speaker, our keynote speaker today is Thomas Kleinteich from TPW Prüfzentrum GmbH in Neuss.
Yes.
So that's you. And before we start, ladies and gentlemen, the presentation, let's first meet Thomas. Thomas, I can imagine that after you studied, you did not get the function as you have today in quality measurement of these parts with the CT scan.
No.
How did your career started?
Well, so I actually started as a biologist.
Biologist?
I was always interested in animals and nature, and so I started biology. And well, one of the key interests I had as a biologist was looking into animals and to learn about their anatomy. And as you know, there's this CT used in human medicine. And so I used CT imaging then to look at smaller animals, and so I came quickly to micro CT. This was about 16 years ago from now.
And micro CT is something different than CT?
Well, yes, it's a question of scale, basically. Micro CT is when you think about structures or resolution in the micrometer scale for small things.
So CT is quite accurate.
CT can be quite accurate depending on the parts you look at. Yes.
But I also understood you did quite some research both in Germany as in the United States.
Yes, exactly.
Tell us about that.
So before I worked at TPW, I worked as a researcher. So I did a PhD in Hamburg, then I got a postdoc position at the University of Washington in Seattle. Actually, I lived on a small island north of Seattle, which we had a focus on marine biology, and I was looking at biomechanics of, well, mostly of amphibians, but also of fishes, and so how animals interact in their environment, considering their anatomy, the anatomical features.
But CT scanning, the technology behind it, that is what interests you.
Yes.
And that's what you turned over into, use it for industrial parts made via additive manufacturing, which is quite different than non-additive manufacturing.
Yes. Well, I wouldn't say it's too different. So actually, the first time I got in touch with additive manufacturing was as a biologist as well. So I had CT scans of very small animals. They were like, maybe the heads of these animals were only a centimeter in length, so more than the tip of a thumb. And so then I 3D printed them in a much upscaled version to get a much better impression of them. And also, like, the physics of CT imaging is the same if you look at animals or if you look at industrial parts. And I guess what's more important is to have some interest in the background. So what you can see in the image and what you cannot see, what's the physical parameters, and
Because most people probably know CT scan from hospitals when they maybe were a patient and had to go into a CT scanner.
Yes.
How it works, you're going to tell us now in your presentation.
Yes.
Well, this presentation is done in two parts. After this first part, it's a small, not a real break, but we offer you the possibility to interact with some questions you're going to send to you. I will tell you more about that later. And completely after the second part of the presentation, then we have space for questions you can put via your screen and chat to us, and we'll ask them to Thomas to answer them. And if not, all questions will be answered. They will be answered on the website of the Knowledge Sharing Center website later on. Also at the end, I'm going to tell you more about at the end of this presentation, there will be a kind of quiz online. You have 2 weeks to go to answer the questions. And of course, we have a nice prize, which will be that the winner will have the opportunity at your company to scan a product. That's the end of this presentation.
Or some personal item you always wanted to look inside. So it doesn't have to be an actual.
Very exciting.
Can be. It just should fit into the CTs. It shouldn't be too large or from a material that we cannot look through. But we can sort these details out.
Okay. Now we're going to start with the first part of your presentation. Thomas, the floor is yours. Good luck.
Yes. Thank you very much. So where did we get? We've been here. So yes, again, thank you very much for having me here. And so to give me the chance to talk about 3D or CT inspection, non-destructive inspections of additively manufactured parts, and with a focus, yes, of 3D printed parts. So the company I work for, TPW Prüfzentrum, we are a service provider for destructive and non-destructive testing. So we don't sell any inspection equipment, so I won't try to sell any CT scanners here. What we do is, so we provide the service. So customers approach us, they have a question about the product, they want to look inside, and then we can provide this inspection as the service we do. TPW itself is a company that was founded in 1980, so we're 42 years now. And originally we were founded as a subsidiary of Spatial Boiler Tubes, which is a company that is trading with tubes, as it says, with pressure tubes. And so TPW originated as the quality inspection part of this company. So they were mostly interested in the material inspection for these tubes to see if the quality of the tubes they were selling is fine. And then and this is how TPW originated. Currently, so we're still a small company. We have around 20 employees. If you want to try from Feldhoven, where we're currently at, to TPW, it's just a little bit more than a 1-hour drive, so we're very close to Düsseldorf, in a German town called Neuss. And yeah, and as I said, so we're a service provider, so we provide several inspection tasks as a service. One of them is X-ray imaging. Then there's also ultrasonic testing, there's dye penetrant testing, there's magnetic particle testing. And we also look at things under the microscope, do metallographic inspection, and sometimes we destroy things by doing tensile and hardness tests. And there's even more than this, and one of the things we also do, and that's what you may know us from, is CT imaging. And so CT imaging in the medical world is known for a rather long time. In industry, it might have started like 15 to 20 years ago. And TPW was one of the first service providers that provided CT imaging as a service to customers. And so by now we have several CT systems available. You can see these systems here on the top of the screen. So that's the large CT we have available. That TPW basically fills an own bunker. And we also have a smaller one. It's called the nanotome, with a high resolution nanofocused X-ray source. And yeah, and so these CT systems have different X-ray sources, different detectors, so they are kind of optimized for different tasks. And with the range of CT systems we have available at TPW, we actually can cover a wide range of CT imaging application for our customers. Also, something that we do sometimes besides the service inspections that we do is that we participate in research projects. So we're currently interested in one research project that deals with quality inspection of additively manufactured parts. In this case, it's about aerospace, but also the same applies, of course, to other fields of industry. And so maybe some of the ideas I will share towards the end of this presentation. Some of this originates also from this research that we do, but also might be applied to the parts that are of interest for you that you would like to look at. Now, as mentioned, so we will be talking about additive manufacturing and quality control of additive manufacturing. And if you think about additive manufacturing, so you might simply think of, you have some powder substrate, and then you have a 3D printer that prints the product, and you get the finished product out of the powder. In real life, of course, this process is much more complicated, and it fills a full process chain, and different steps during this process chain, of course, have different parameters that can be optimized, so it can become quite complicated. So if you just think of the powder, you may have to consider which material you want to use, What's the characteristics of the powder? What's the shape of the powder? Is there any porosity in the particles already? If you think then about the printing process, the AM process, you have to think about the machine you'll be using and the LPBF parameters. So the actual machine parameters to build something. In many cases, the sample will be post-processed, so what you get out of the printer won't be the finished product, but it's kind of like the pre-step to the finished product. So you have to think about cleaning the part, removing support structures, remove powder remains, machining, heat processing, and so on. And then in the end, if you have the finished product, often it just stands for it itself. It has to be assembled with our products, of our components to build a larger structure. Now, during my presentation, I'm trying to bring these two things together. So I'm bringing together CT imaging that we do as a service for our customers and additive manufacturing. And so I will talk about, or I will provide some information on basic principles of CT imaging. So what's the physics behind CT? This, of course, comes with some limitations. So what can be seen in a CT data set and what cannot be seen in a CT data set. And I will also apply some ideas on how to apply CT to the AM process chain. Now, let's start with some basic physics of CT imaging. And, well, as you might be aware of, CT in itself, it's a kind of X-ray inspection. So we use X-rays to generate CT data sets. And so what applies to X-ray imaging also applies to CT imaging. And so this is a very basic scheme of how an X-ray inspection might work like. So we do have an X-ray source that would be an X-ray tube that generates X-rays. We do have a part that needs to be inspected, so that we want to look at, where we're interested in the properties of the part, and we capture the X-ray image of this part on a detector, or more in a classical way on an X-ray film. And what we see on this film or on this detector is an X-ray projection image of the part. So now, just keep this scheme in mind for the rest of this presentation, as I will come back to this quite often, I think. And now, this image for each of you, so even if you don't have a background in biology, or if you don't have a background in X-ray imaging, you'll immediately understand what this picture is about. So it's an animal, it's a dog, and this poor animal swallowed a keychain that you can actually see here inside the animal. So there you go. And now, but how can you see this? And this picture is made by seeing dark regions in which X-rays have not been absorbed while they passed through the sample, so to say. In this case, it's the dog. And bright are regions in which X-rays have been absorbed and less X-rays hit the detector behind the sample or behind the animal, and less X-rays have darkened the film, basically. So, and this is why, so if you see the metal, it's really bright. So metal absorbs more X-rays than, for instance, the musculature in this dog, where X-rays more or less just pass through, and bones are somewhere in between. And so this is how the contrast in this image is made, just by the differences in the X-ray attenuation or in the X-ray absorption of the different materials. And physically, this is described by Lambert-Bear's law. And so don't be afraid, this won't be a classic physics lecture, so I won't put too many equations in here. But I just want to show this one equation to give you an idea on what is working and what's not working in CT imaging and what are limitations. And so basically it's described what the X-ray image we see. If you look at the I, would be the intensity of the X-rays that I capture on the film or on the detector. I0 would be the original intensity of what we have at the source, so the X-ray source we're using. And then there's an exponential decrease which decreases with a factor of mu, and d is the material thickness. And most important is this parameter mu. And the mu is the linear attenuation coefficient of the material we're looking at. And in here it's a constant. There's the wavelength of the X-rays we're using. So the longer the wavelength, the less energy the X-rays have, the higher is the X-ray absorption, and the stronger will be the decrease in signal beam. And most importantly, what you see here is Z, which is the atomic number of the elements in the material. So the atomic number goes into this attenuation coefficients by the cube. And this is exactly why you have differences in the material in the way they absorb the X-rays. It just depends on the atomic number of the elements that are in there. And while this is just physics, it also shows some really limitation that we have for a CT scan. In order to get a CT scan, we first have to capture X-ray images of the sample. And we only can capture X-ray images of samples that we can pass through with X-rays. And how well this works depends on the wall thickness of the parts, and it also depends on the atomic number of the materials that we look at. And well, you all know this, that you cannot look for any material by using X-ray radiation. So you may know that Superman cannot see through lead. And I have no good reference if Superman could see through Inconel, but I would guess he would have problems seeing through 300 millimeters of Inconel as well, because the atomic number of Inconel is rather high. Of nickel will be the atomic number of 28. And so if you have a large chunk of material with a high atomic number, you just cannot penetrate this with Inconel. And now the truth is, most people, if you look at CT, what works really well is carbon-based polymers, so plastics. Carbon has an atomic number of only 6. What works well too is aluminum, which only has an atomic number of 13, and which still works not as well as aluminum, but it's still possible to get a decent image quality. Smaller parts of titanium. Titanium has an atomic number of 22. And now if you are critical and you look at like advertisements of CT imaging systems and so on, you could guess that most of the nice 3D images you see are made from aluminum or plastic parts, because there you always have a good image quality, because it's quite easy to scan through them. And I have to admit, I'm not different than most of my colleagues in CT imaging are. So what you see here and what you will see through most of the presentation is an example from this additively manufactured part, which is made from aluminum as well. So but just to give you an idea what's the dimensions of these parts, a part of this size can still be studied decently with a CT. Yeah, if it's made from aluminum. The same part made from steel, we would really have issues to CT scan such a part. But with aluminum, it works quite well. So, and what you see here in this picture, actually it's not a CT scan of this part, it's just an X-ray image of the part. And you can already learn something by just looking at these X-ray images. So there are questions where you don't necessarily need to have a CT scan. There are questions that you can just answer by looking at an X-ray image. And one of these questions might be, so if there's still supportive structures, or are there large accumulations of powder inside this part? So you can visualize these already just in one X-ray image of such a part. Like here you see, yeah, these are the remains of the supportive structure that you can see there. Now, there's also things that you cannot see in an X-ray image. If you look at another region of the part, if you look at this region, you see there's like 2 channels in here. There's one channel here, and there will be one channel here. Now, if you look at the actual part, you'll actually see that there's 4 different channels. So it's 1, 2, 3, 4. And because this is just a 2D projection of the whole geometry in one single plane of projection, you have 1 and 2 lying on top of each other, and you have 3 and 4 lying on top of each other. So the problem with these individual X-ray images is that you lack the 3D information of the part you're looking at. And now thinking of additive manufacturing, where you manufacture complex 3D geometries that you couldn't even think of manufacturing like 15, 20 years ago, the more complex the 3D geometry is, the more important it will be to have this 3D information captured by your inspection method. And so the idea would be to have, if you have a part and you capture an X-ray projection and you cannot tell the 3D geometry, to look at from the part from different directions. So to capture X-ray images from different views of the part. And this is exactly what computed tomography does. So for a CT scan, we do have the same setup as for an X-ray study. We do have an X-ray source. We have the part to be inspected. We have some detector, and we capture projection images. But what we do for a CT is we rotate the part by 360 degrees. And so we capture X-ray images while the part is rotating by 360 degrees. So CT is simply based on capturing X-ray projections of a rotating sample. And what a CT scanner actually sees is what you can see here on the screen. So it's X-ray projections of a rotating sample. So you have the sample that I just showed before. You see X-ray images from different points of view. And it's the same in human medicine. So there you all know that the CT scanner looks like a tube, and the patient lies in the tube, and then you have the X-ray setup rotating around the patient. In industry, it works a bit different because we actually can rotate the samples we're looking at. So you couldn't rotate the patient in the hospital, but we can rotate the samples we look at. And so the setup of an industrial CT looks a bit different to a medical CT, but the basic principle of capturing X-ray images of a rotating sample, it's pretty much the same. And now in the next step, and this is often mistaken, so sometimes customers ask us, and they seem to be thinking that a CT somehow virtually slices the sample by using X-rays. So that's not the case. So what the CT does, it captures X-ray images, and then in the second step, it reconstructs the 3D information of the volume of the part that was CT scanned based on these X-ray projections. So this reconstruction is done on the computer. So it's a post-processing step, and the full 3D volume of the part is then reconstructed from these X-ray projections. So, and then this is then the step after you have the reconstructed data set. Then you can start virtually slicing through this reconstructed 3D volume of the part. So it's not that we slice by using X-rays and then build this together to a 3D model. It's rather that we reconstruct the 3D volume based on X-ray images, and then this 3D volume can be sliced in the post-processing steps after that. And this slicing can be done totally arbitrarily. So I can redefine planes of sections. I can go from front to back, from top to bottom, from left to right. I'm really free in how I slice the part, what I look at. And this can be quite powerful, as you can virtually slice through the part. You get thousands of sections just as if you would slice it and look at it under a microscope. And so this is an example. So that's just a slice movie through the aluminum part that I just showed you. It goes from the top to the bottom, and you nicely see the geometry of the part. And if you would zoom closely in, you would also see the material properties or some voids and cracks and things like that if they were present. Because that's the actual part. So it's not slicing through a 3D model of the part or a CAD model. It's slicing through the actual part without destroying it. And now this can be used to check for porosity. As I said, this can be used to check for remains of powder in additively manufactured parts. This can be used to check for cracks or lacks of fusion that you may see in additive manufactured parts, or for inclusions of foreign particles that differ in their X-ray attenuation from the base material, so that you have a have a nice contrast as here. So you see this particle has a higher X-ray attenuation than the base material, and that's why it's shown so brightly. There's post-processing steps where you can apply software algorithms to a CT data set to automatically detect for porosity, for voids. You can also detect automatically for foreign particle inclusions. We can CT scan powders at very high resolution. So you see there's individual powder particles. Here there's a measurement, it says 15 micrometers, so that's a 55 micrometer powder particle. And then we can visualize also foreign particle contaminations in powders, but we also can visualize porosity in powder particles. And of course, since CT also captures the 3D volume of the particles, we can study particle size distributions, we can get the volumes of the particle, the shape of the particles. We can CT scan full assembled parts and check for the assembly. So that's an example of a flashlight. You can see where it's quite simple scenario, but you can see where the batteries are. You can check the switches. You can check if you switch it on and off, so how the position of the switch will change, and so on. And again, as we capture 3D geometry of parts, we can also use CT for metrology applications. So we do have the full information on the part geometry, and we can measure diameters, distances, lengths, shape variables. And now we can compare the 3D geometry of the actual part against the CAD file. And the big advantage of CT over other measurement methods, like optical surface scans or tactile measurements, is that we have a direct access also to internal features, because we captured the full 3D geometry as the whole of the part, including internal features. So we can also measure internal features just as we can measure based from the surface. And so you see there's a whole range of post-processing steps that can be done on a CT data set. And so CT can be a quite versatile tool that can be used for different topics, for checking the assembly, the material health, the shape of things, metrology, and so on. And this all basically is different kinds of digital image processing. And here, well, one name you will come across when working with CT scans is Volume Graphics, which is a German company from Heidelberg. And they offer a CT inspection software, and they also offer on top different add-on modules that can be applied to CT data. And actually all you see here in the slides, like the porosity check or the shape comparison against CAD, these are all available as add-on modules for the Volume Graphics software. And so now this is just to let you know, so we're also a distributor of Volume Graphics software. So in case you are interested in acquiring this software, we can also make this available through TPV. And the question often comes up, and I will talk a little bit about this soon. What's actually the difference between the full version of the VG Studio full version and the freely available MyVGL view? Yes.
Okay, Thomas, thank you so far for your presentation. This is only the first part.
Yes.
And I can imagine maybe one question in between. The machinery you use is quite expensive.
Yes.
Is such a scan of such a product also expensive? Can you give us an idea about cost to scan at one time, for instance?
Well, it's always hard to answer, but like as a general rule of thumb, for a one-time scan, I'd say, for the scan of such a part that I just showed, I also my presentation will be in the range of 200 to 300 euros.
But that's not, in my opinion, not so expensive.
But it always depends on the questions you're asking. So if you look for a serial inspection and you want to have like thousands of parts scanned in no matter of time, then probably you wouldn't scan this at the best possible resolution. You would rather optimize the process to a particular question. and the price can be very variable. Or on the other hand, you might want to see like the tiniest pore where we have to go into more detail, which may make the scan more expensive. So it's always quite hard to give
It sounds to me very affordable.
It's a lot of interaction, what the customer actually wants to see and what will be inspected.
Okay.
Yes.
Thank you for this first part. Now,
Yeah,
ladies and gentlemen, we're going to do a small, not a real quiz, but we are going to interact with you. And you see on the screen projected a QR code. And if you now use your phone, your smartphone, to the QR scanner, I will do that now right away. You see. It will pick up a tool called Mentimeter, and you will be right away directed to a question you can answer with words. And if you do that, we see on our screen as well the results of all your answers, and we will ask Thomas to react on that one, because the question is, where have you ever come across CT scan before? Let's now maybe exclude the hospital, of course, and maybe all the other cases. Did you already come across CT scan in your daily life, being in industry active, manufacturing parts, inspecting parts, etc. So let's see what people say, Thomas. Hospital is there.
Hospital is obvious. So archaeology and geology is an interesting field. So it's kind of my background. So as I say, I started in biology. And definitely it's used in science to study objects of different questions.
From your profession, do you have an idea how many % of the manufacturing industry is already using this technology? Is it 1%, 5%, 10%? It's new.
I couldn't tell.
No.
It's quite hard. So what we typically see is that many of our customers, so what we often come in touch with is like prototypes, first article inspections, things like that. And then if you move more towards production scenarios, that well, either there's more confidence in the parts being built, that they are inspected in other ways, or maybe not inspected at all, but that the CT typically is used for smaller batch sizes.
You're looking for confirmation that you did something right or wrong.
But that's actually changing a lot. Like also with additive manufacturing, as there's not as much of a database to build on, so it's more and more moving towards a serial production as well.
Okay. Let's see if new words come across. Not anymore at this moment. We'll leave this for this moment. Now we'll go to the second question. Which part comes to your mind first when you want to have a part scanned, private or business? Just let's see what the audience would like to scan by you and that have scanned. Can be anything. Just come up with your part, what you think, dear audience, which might be interesting to put into a CT scanner and to see what the results are. Okay, we'll wait for your answers. Okay. You see already business coming up?
No.
Density variety, fluid transport manifold. You can choose the applications which are offered to you in the app.
Cooling
bodies with tiny channels.
Yes, that's something that's
sounds familiar.
Yes, it's all these
manifolds
sound familiar so far. For porosities.
Porosity study.
Thin wall titanium, yes.
Quite a different list.
Yes.
Vulcanized parts, thin wall titanium
parts. It's mostly business, I'd say.
Yeah.
Because no one has like thin wall titanium parts at home.
Oh, yeah. So it's business, yes. But even later on, when you win the prize of the quiz online, you can even have a part scanned of your private collection at home. So that's also possible.
That's possible, yes.
That's what we told up front. Okay, so there's a variety, Thomas, what people answer, private or business, and what kind of business. It sounds familiar to you? You recognize it in your daily practice?
Yes, yeah, I do. Okay. And now the watch comes. This would be like one of my personal items as well. Would put on the watch, car keys, Rubik's Cube.
To see how it works.
If you always wanted to see how it works.
To find the trick how it works.
Yeah.
Okay, kind of reverse engineering. Yeah. Okay. Well, thank you for your answers, dear audience, for this. And now we are going to proceed for the second part of the presentation. And Thomas is going to show you live some software. Now we switched already to the right screen. Thomas,
Yes.
the floor is again yours. Good luck.
Okay, thank you. So yeah, now what you see here is again the aluminum sample part that I brought you, and the data set, the CT data set, is open in the volume graphics software, which is Studio Max. What you have available is the different planes of sections. So I can actually zoom in here. I can slice through the part and look for anything that I might find interesting. I can, for instance, see suspicious structure here. I can then place a marker and zoom in from different angles. And also what you see is the 3D model of the part, which here in this case has already been virtually sliced, but I can also remove this. And now what we then do with such a data set, for instance, is that we also load the CAD information into the part or into the scene. And then we can compare. So what you see now is the green line would be the CAD file, and I'll switch on the white line, which refers to the surface of the actual part. And then you can measure automatically over the full surface of the part the actual to nominal comparison. So you can measure the difference between the CAD file and the actual part. And so all this is stored in this in this scene. And so you get the false color-coded representation of the part. And then what I said, so that's something you can also do with optical measurement methods, but what's the advantage of CT is that I can basically just slice through the part, and with the same effort as I would measure the outside of the part, I also get information on the inside of the part. And so I get a nice overview of the internal geometry and the deviations of the internal geometry compared to the CAD data. And so the software, if you just click on this analysis, gives you all kinds of statistics. So for instance, you see over the full surface, over the full 3D surface of the part, also considering internal features, you see the deviation distribution. So how much does the actual part derive from the CAD file over the full 3D surface? And you can also look at this in an accumulated view. And then you can prepare annotations where you basically, I cannot see it because I'm in the remote, but I can show you like this, where you basically set a marker at a particular region and you get a measurement of the deviation in this particular area. And so like this. And so this would be the what I showed is the full version of VG Studio Max. And then there's the freely available MyVGL software. And so I'll close this. I won't save this now. And now I'm open the data set again, but now I open it with the freely available MyVGL. And so this is a viewer that everyone can download. And so our customers typically download it to look at the data that we share with them, that we generate for them. So it takes a second to load. I have to be a bit patient. So patience is a big thing when working with CT data, because as you can see, the data set here, I just showed you, it's 5.4 gigabytes large. So handling data and looking at progress bars in software is a part of our daily business. Well, I don't know why it's taking so long, but it's also only on my laptop computer, which certainly is not as powerful as a graphics workstation you would typically use. But here we go. And now I go in MyVGL, say open project. Here it's asking me, so I actually could uncheck some analysis to free up some memory, which I'm not doing at the moment. I'm just loading the full data set. And so now it's loading the 5.4 gigabytes into the into the memory of the computer with the MyVGL software. And so this is something you could, as our customer, you could do with the scan data that we provide. And you will also have to learn some patience if you're doing this. And now what you see, it basically looks exactly the same as the full version of the software just looked like. So you have some buttons less on this side of the screen, and there's also some fewer buttons on the top. But generally, so to browse through the CT scan data, you can also do this with the freely available MyVGL viewer. You can also place markers and jump to different regions of the data set. So it's all possible in the free version of the software as well. Can jump here to look at these remains of supportive structures. And if we applied an analysis to the data set, you can also load this analysis in MyVGL, or open the analysis in MyVGL and do exactly the same. So everything that I stored in the full version in this project is still there, also if you open it in the free version of MyVGL. And also the analysis results, so you cannot actually change the analysis, so that's all gray out. But the results of the analysis, the histogram and the accumulated histogram, and the markers that I might have defined before, all this is also available with the free version of the software. So you just cannot redo these analyses. So you could change the markers, but if you close the software, these changes will be gone again because it's just a viewer software. But as a first step to look at data that we generate and to learn about your parts by like browsing through the images, I think this free version is also very powerful to be used. And then once you're experienced and you really know what would be the tweaks that you would like to use in the software, then you probably might think about switching to the full version. But like for looking at the data and for looking at analysis that have been applied to the data, the free version is very powerful as well. Okay, and so with this, I will go back to the actual PowerPoint presentation, because very important point about working with CT data and applying analysis to the data is this all depends on image quality. So it doesn't make sense to apply a shape inspection to a CT scan where you can barely see the shape of the part because the image quality is so poor. Or to apply a porosity inspection to a part where the resolution is so poor that you cannot resolve the pores in their size. So all this depends on image quality. And so the rest of the presentation will be mostly about image quality and then also on AM parts on the process chain. And as a basic understanding for what a CT scan is, you have to understand that the slice images that we'll look at when we zoom into the CT scan data are actually pixel images. So if you really zoom further and further and further, at some point you will see individual pixels in the CT data set. And now in CT, we're talking about 3D volumes. So if you have a slice image, it's a pixel, but if you think about the full 3D volume of the part, it's actually a 3D pixel. And this is what the basic unit of a CT scan is. It's called a voxel, which is a volumetric pixel. So a 3D volume is built from volumetric pixels. And if you look at this line of cars down here, so that's if you have kids that play with different sizes of Lego bricks, you may actually know this kind of pattern. So if you have only large voxels, or if you have only large Lego bricks, then you can build much less detail than if you have really small voxels that you can build much more detail in a smaller area. So what is crucial for the spatial resolution of a CT scan is the size of individual voxels. So it's the voxel size, and many of you probably are aware of this. Now, voxel size is nothing that you can infinitively increase or decrease. So there's quite strong limitations on what the voxel size of a CT scan can be. And most determining of the voxel size, so what will be the resulting voxel size of the scan, is the CT scanner hardware that you use, mostly the detector of the CT scanner, and the size of the sample, because you project the sample onto the detector, so to get an X-ray image of the sample. So, and it's actually quite simple. So to estimate the voxel size, so what would be the size of each voxel for such a scan, you basically have to divide the dimension of the part by the number of pixels you have along this longest dimension of the part. So for the part that I showed before, so if you think of a part that has dimensions of 230 times 110 times 70 millimeter, which is the aluminum part I showed you in the beginning. And typically detectors in CT scanners have 2000 times 2000 pixels. There's some detectors with 4000 times 4000 pixels, but these are also not yet state of the art, or not very wide distributed. What you get in the end, so if you use the 230 millimeter of the part divided by 2000 pixels that you have available on the detector, each pixel will be in the range of 0.115 millimeter, which would be 115 micrometer. And this will be also the resulting voxel size of your scan. So for such a part, you will be restricted to a voxel size somewhere in the range of 0.1, 0.15 millimeters. Now, you all know this actually, so it's not different than taking a photo with a digital camera, just like the camera in a cell phone. This is just to give you more insight on this principle. So this is just two pictures that I took with the same camera from a bunch of pens that were lying on the table. So now I can either move the camera a bit more away and capture the full pack of pens that are lying there, or I can move the camera a bit closer and focus on some detail. And of course, in the left picture, I have a per millimeter pen. I have less pixels than I have on the right side. So this would be a high resolution option. This is a low resolution option, but the number of pixels in these images is totally identical because it's based on the same camera and the same detector that is built on the same sensor that is built in the camera. And now if I want to zoom in, of course, if I'm on the left side where I have the full pack, the wide field of view, I get much less detail than if I zoom in to the right. So here I see much more detail as I have more pixels available to still zoom in, which I don't have available. And sometimes, if samples are quite small, we can play a bit with the voxel size to tune the CT scan to different demands, often in terms of the cost of the scan and the required resolution. So that's just an example from a density cube that you may know from additive manufacturing. So these cubes are often printed with the actual parts to give some idea on the material quality that is printed. And typically these cubes have a dimension of 10 by 10 by 10 millimeters. And if we CT scan a 10 by 10 by 10 cube, the resulting voxel size for such a CT scan will be in the range of 7 micrometers. Sometimes customers say, well, I don't need to have a 7 micron resolution. The resolution can be worse, so the voxel size can be higher. We actually could place 3 samples in the same scan, then virtually increasing the part dimension. So instead of 10 by 10 by 10, this would be in one dimension, it would be 50 with some gaps in between. And then the resulting voxel size will be 24 micron. It's the same machine, the same detector. I just zoomed further out here, have a wider field of view and can fit more samples into it, but on the expense of having less spatial resolution in the resulting data set. And this also has some impact on the quality of the picture you see in the end. So this is the example that is just one slice through the CT data set of the cube at the voxel size of 7 micron. You can see some porosity towards the edges. This is the same scan at a voxel size of 24 micrometers. So at the lower resolution, you can still see these rather large pores. So in this case, it's not much of an issue. However, if you focus on like really small details, so like this tiny pore that can barely be resolved in the 7 micrometer data set, such details will simply disappear, because when they get smaller than the voxel size of the data set, so if the voxel size is larger than the detail you're looking at, the detail will just disappear because it's smaller than the base unit of your scan. It's below your spatial resolution. And now this brings up a very important limitation of a CT scan. So a CT scan definitely has a resolution limit. So any inspection method has some resolution limit. So you cannot have one inspection method that gives you a spatial resolution from the scale of an atom to something really large. You always have to operate in a certain range. And in a CT scan, so if you think of detecting pores or cracks, any kind of void in a CT data set, you have to think about what is the voxel size of the scan, and what would be the size of the structure you're trying to find. And now if you think of a structure that is smaller than the voxel size of your scan, it will be impossible to detect in a CT scan. Now if you have a structure that is exactly the size of a voxel, by coincidence, you might get lucky to find it, but the probability to find it is rather low. If you have a structure that is like 2 times the voxel size, the probability to detect it will be higher than if you go to 3 times the voxel size and so on. So it's good to think in terms of a probability of detection for voids when thinking about CT data. If you have a very, very noisy scan where you cannot barely see any of the internal geometry of the part, of course, you will also have a very low probability to detect voids. If you have a very nice scan, you can have a much better understanding of finding small structure, a better chance to find small structures. But just never 100% guarantee that you actually will find something. And so there's one standard in CT imaging, the DIN ISO 15708, which actually recommends that the smallest feature that can be detected in a CT scan should be in the range of 2 to 3 voxels. So in other words, if you have, for instance, a 20 micrometer CT scan, the smallest features you will be able to detect are somewhere in the range of 40 to 60 microns. If you go below that, the chance is very high that you will miss those. And one thing that always comes up also with our customers, and it's a really common problem, is the amounts of data that we generate. And of course, if you go to a high resolution CT scan, this comes with very high amounts of data. And now just think back of the part that I just showed you, the aluminum part. If we CT scan this with a voxel size of 150 micrometer. Now it's a little bit of math, but it's actually quite simple. So if you have a part that's 230 times 110 times 70 millimeters, and we want to rebuild this part from voxels, and each voxel has 115 micrometers. So we need 2,000 voxels to cover the 230 millimeter length. We need 957 voxels to cover the 110 millimeter width. And we need to have 609 voxels to cover the 70 millimeter depth of the cell. Now in the volume, this comes down to 1,165,626,000 voxels. Each of these voxels has some gray value assigned to it, and the gray values are in the range of 16-bit. So it's 2 exponential 16, which is 65,000 something gray values that go from black to white. And so with 16-bit gray values, means that each voxel takes up 2 bytes of information for data storage. So the data set size for this part scanned at the voxel resolution at 115 micron will be in the range of 2.17 gigabytes, which is still, well, it's too large to be shared with an email, but it's still in a range that you could nowadays upload to a cloud storage and send the customer a link to download it on the other end. Of course, if you want to expect 10 parts, then it will be 21 gigabytes. So it's scaling up quite fast. And now, for instance, you want to switch to a modern 4K detector, or you want us to perform several scans of different regions of the part at a higher resolution of 58 microns instead of 115 microns. So basically doubling the resolution of this data set. So this will mean that instead of 2,000 voxels along the length of the sample, I will need to have 4,000 voxels. And then I need 1,914 voxels for the depth and 1,218 voxels for the width, which comes up to more than 9 billion voxels. Again, each codes for 16 bits, and the data set size will be 17 gigabytes instead of just 2. So as a rule of thumb, by reducing the voxel size by a factor of 2, like doubling the resolution, I increase the size of the data set by a factor of 8. And 17 gigabytes is still something we can handle, but it really gets much slower, and it makes a big difference if you have to wait 1 minute to load a data set or if they have to wait 8 minutes. And also anything that comes on post-processing later on takes much longer as well. And so we're also struggling sometimes with these large amounts of data as these slow down the post-processing steps. So if a defect analysis on a small data set takes like 2 minutes, suddenly it will be 16 minutes or something. And then we do this 10 times, and then half the day is just gone by trying to handle these amounts of data. But that's just to keep in mind. So something that's just not practical at all to focus on high resolution only. It's more important to think about the questions you're interested in. And besides resolution itself, what is often forgotten is that the detectability of details also depends on the contrast in the data set and the signal to noise ratio. And this is where Superman comes back. So if you have a part that is made from lead and you cannot get even an X-ray image of this part, all your CT data set will be just noise, and you don't have to think about the spatial resolution of such a data set, because if it's just noise, then you will not see anything at all. And so contrast and signal to noise ratio are also important measures, even for the not as intuitive as pure voxel resolution. And just to give you some examples. So if I want to look for powder that is trapped in some channels of a 3D printed aluminum part, this will work really well because I will have powder versus air. I have a good contrast, it's aluminum, it's no issue at all to CT scan. I have a good signal to noise ratio, I will be very likely to see the powder. If I will look at carbon fibers in a carbon polymer, I will have a really poor contrast because I'm basically trying to find carbon in carbon, and I don't have any difference in X-ray attenuation between the fiber and the base material. So I have a really poor contrast, and even for anything that's plastic material, that's polymer can be quite easy to scan, as it's quite easy to penetrate with X-rays. I have perfect signal to noise ratio, but I have such a poor contrast between fiber and base material that I won't detect those fibers, or will have a hard time detecting those, also independent of the resolution. And another example would be gas porosity in an Inconel housing. If I look at air versus Inconel, I will have a fantastic contrast, but as Inconel is hard to study by X-rays, I will have a poor signal to noise ratio, and again, there might be so much noise that I won't be able to see the structures I'm interested in at all. Now this brings up a more or less philosophical question, which customers often ask. So how can you be sure that you're not missing anything in the CT data? And it's really impossible to prove that something is not there. So absence of evidence is not evidence of absence. So for me as an inspector, I'm always happy if I find something, because if I find some porosity and cracks and so on, I can show, well, the scan is good. I can visualize these structures. And if I find a large pore, I don't have to worry about small pores that I won't see. But it's really getting more complicated if you move towards smaller samples or towards smaller voids that one can barely visualize if you have to find those. And so what is definitely a topic in the world of computed tomography is to find measures to quantify which features are still visible in a scan and which are not. And there is quality indicators commonly used in other non-destructive inspection methods, such as X-ray imaging and ultrasonic imaging, ultrasonic testing. But there's no generally defined CT image quality indicator. And that, for me, actually, it's a great chance for additive manufacturing. I just want to show you an example here. So I talked about these inspections of density cubes before that are printed with the actual parts during the 3D printed process. And so we can process these density cubes at a very high resolution in the range of 7 microns. Which will allow us to detect voids in the range of 15 microns and above. And now if you have a rather large part where we cannot reach this high resolution, but you printed a density cube, or you prepared a density cube with some artificial voids, or you printed the density cubes with parameters where you are sure that these parameters aren't perfect to build such a structure, so it's very likely that there's voids in there. We can actually qualify the size of the voids by CT scanning the density cube itself at the high resolution. And then we place the same cube into the scan with the actual part at the lower resolution and have some idea which voids we still see and which we would also see in the part and which kind of voids we are missing. And that's the basic principle as this example that I showed here before with the 2 different resolution scans of the same cube. So here in this case, I know for the 24 micron scan that there is a pore which I just cannot see. And so I could have some indirect estimate which size of structures I still can visualize in the scan of the actual part and which not. And now to come to an end towards my presentation, of course there's different requirements and possibilities for CT along the AM process chain, besides being used for image quality indicators. So as I said early on, so we can inspect powders by using CT, powder substrate, so you can actually, at the first step before you even throw the powder into the printer, we can have a look at it, check the particle shape, check for porosity, and so on. And for the powder, as we want to have a very high resolution scan, we're aiming for voxel sizes in the range of 1 micrometer. So we're looking at very, very small samples. So really trying to maximize the resolution. Now, another example for the AM process chain and during the actual AM process to quantify the AM process would be the inspection of density cubes. This could provide insights on the distribution of void over the entire volume of the cube. And so far what is often done when these cubes are printed is that people look at one particular plane of section of these cubes with metallographic inspection methods, so basically under a microscope. So there's one plane of section you're looking at under the microscope, which neglects the 3D volume of the cube itself. Often that's not very problematic, but I can show you a nice example where this might become an issue. So this is a cube that seems to be in perfect shape. So and if you would just cut it like here, you would see no voids at all. But if you really pay attention, so there's like one particular plane of section. There's just one section in the entire cube where we found such a lack of fusion that makes up a quite substantial part of this section. So that's actually a nice example. So if you would do a metallographic inspection of such a cube, you probably would just cut it in half in the center, and you would miss this particular lack of fusion in the part. And so if you printed this cube next to your part, I guess you're quite likely to also have such a structure applied to the part that was printed next to the cube. And you would just miss the structure. So we're way more likely to find voids. And yeah, so okay. And then before you actually do the post-processing, that's what many customers already do with us, is you can CT scan the raw part to look for, well, for really severe voids in the part, or you could check for the powder removal before you do a heat treatment and so on. So you could save money by just looking at the part before even pushing the post-processing any further. And often this can be done at the lower resolution as well. So this doesn't always have to be the highest quality scan at this stage. So if you're just interested in cross accumulations of powder in the part, we could even scan these parts on the build plate and then scan like 3 parts in one scan at the low resolution, of course. You wouldn't see the smallest void or the smallest crack in the material, but you still get a very good idea if there's still powder in there. So it always depends on the specific question. And then, of course, if you look at the last step of the AM process chain, you can do a CT scan of the finished product, and then you can do the measurements, compare against the CAD file, and look for the quality of the finished or of the final post-processing, and so on. So to sum this up, so I started in the beginning, I'd like to provide some information on basic principles of CT. I will talk about physical limitations of CT and also on ideas to apply CT to AM parts along the different steps at the AM process chain. Just to give you some keywords to remember after the presentation, also for the quiz maybe. So I provided some basic information by talking about X-ray imaging, that CT is capturing X-ray images over a 360-degree rotation. And we talked about the magnification principle, so that the voxel size also depends on the dimensions of the part. Then for the physical limitations, talked about X-ray absorption and scan resolution. And for the ideas to apply CT to the process chain, so talked about powder CT, 3D porosity analysis, and inspection of finished parts. So, and with this, so back to the beginning, so I said we're a service provider, so we don't sell any CT hardware. What we do offer is service, the inspection service, to meet your specific demand. So part of my role is to provide the consulting to fit your defined inspection tasks, and then of course we also do perform the inspection. Yes, and so with this I'm at the end. So there's the contact information, so maybe you want to contact me afterwards, feel free to do so. And yeah, it was a pleasure to give this presentation.
Thank you, Thomas. Kleinteich. Normally you would now hear a big applause. Well, my team will do that as well, and I will invite you as well, ladies and gentlemen, back home to give an applause as well for Thomas, although we can't hear you, but what a story. There's a lot more to say about this technology than many people, I think, expected. And they also have some questions for you. Okay. And I look now to my colleagues in the studio to see, we pick out a couple of questions and we'll try to answer them. And of course, all the questions will be answered on the website of the Knowledge Sharing Center afterwards. So we pick out a couple of these. This is the first one. Can you visualize a gluing layer? And can you see air bubbles in the gluing layer?
Yes.
2 questions.
Yes, and yes. It depends, of course, like always, it depends on the spatial resolution, but we did projects where, for instance, looked at the gluing of some printed circuit boards on a cooling body and so on. And we can visualize the cooling quite well, and you see also the air bubbles in the gluing layer. But again, it depends on the resolution. So if the thickness of the gluing layer is too thin, we won't be able to visualize it. So it depends on the size of the part. So the smaller the part and the thicker the gluing layer, the more likely we are to actually find a plane of section right through it.
Okay, another question. Let's wait for the question. How small can the inclusions be for you to still measure them? It's about accuracy.
So that's basically the point with the 2 to 3 voxels in a best case scenario. So if an inclusion really differs from the base material, so it's a bright white particle, you can detect it quite well. You see it as it's much brighter than the base material. But of course, it has to be larger than 2 voxels in each direction. So let's say for a scan, for instance, that was CT scan at 50 microns, which would correspond to a 100 by 100 by 100 millimeter sample, roughly. The smallest inclusions you can visualize would be in the range of a diameter of 100 microns.
Actually, so customers should start thinking in terms of voxels.
Yes.
Okay. Oh, that's clear. Okay, let's go for the next question. Would you be able to measure surface roughness as well with this method?
Typically not. Like surface roughness really is CT is not really the method of choice for roughness measurements itself. As often roughness profiles themselves are smaller than the resolution of the CT scan data. Unless you have a really rough part where actually the roughness gets into a macroscopic region that is like well represented by individual voxels, then you can measure it. But there's certainly other measurement methods to get a better idea of roughness.
Okay, we go to the next question. Is it possible to freely redefine the CAD file alignment so not only a best fit of the scanned volume?
Yes, yes. So that's basically a software topic. So when we perform a CT scan, you have seen, so we aligned the part, so it was somehow standing at an angle, which is basically to reduce wall thickness that has to be penetrated by X-rays. And then what we always do is we realign the part, for instance, with the CAD file. But we could realign it freely in space, and we also could, there's different registration methods. So we, for instance, could freeze a particular plane and then make sure that the part in the CAD file are aligned on this particular plane, and then you will see deviations in another region. And actually, that's well, an important question. So because often we are asked to do CAD comparisons, and if you do 10 samples and you always use a best fit, and it's not well defined, because if you have 10 samples and you always do a best fit, you may end up with 10 different registrations, as it's always minimizing the differences between CAD and actual part. So it will be quite hard to compare them sometimes. And for instance, if you're looking at a plug or something, you're only interested in the region where it has to fit. And so all this can be done from the software side.
CAD files have a nominal geometry without tolerances.
Yes.
The tolerance is an added feature.
Mm-hmm.
Do you also treat these features if you compare them to your scan files?
If it's in the CAD file, we can, yes, we can.
Intelligence in the CAD file is you can also use that to compare to the scan.
Yes.
Okay, because then maybe it's not the roughness anymore, but as in the former question, but you can compare something anyhow.
Yeah.
Okay. Do you have any more questions for the screen? No, these were the questions we picked out. Are more questions which will be answered on the website, as I told before. If we are looking out to today, Thomas, this is the state of the art.
Yes.
What technology improvement do you wish today to have, which you don't have to meet with your customer requirements? What do you wish?
I wish. Well, it's quite well. Certainly, what will change in the future, what will become better, is data handling. I mean, so I'm not too old, but the first computer I had like 250 megabyte hard drive, and so it would be a joke nowadays. So I guess that's something where the development is really going fast.
Okay.
On computing power, being able to work with larger data set, but on the other hand, also scan resolutions will increase, so you will fill up the spaces you generate with more computing power as well in the future. I guess there will always be the one data set that really pushes the limit to its available computing power.
Are you also collaborating with the suppliers of the equipment of the scanners for further on developments? Maybe you can lay down your wishes to the partners who build these scanners. Is that possible?
To some degree, yes. So computer tomography is a rather small community. So we know the people who built the machines, and we certainly have some interaction with them. But of course, there's many different customers applying CT in different fields. I guess so. What we do as a service provider is that we have a wide range of applications. So we really do CT scan powder, and then the next day we will have an engine of a car or something. And what is very different, for instance, to a manufacturer, who will have one particular part, and then the CT scanner will be optimized for this part. And so I guess for hardware suppliers, there's lots of influences coming in. I guess we may not always have the strongest impact in that regard, but yeah, there's certainly interaction.
What you do today is actually offering CT scan as a service.
Yes.
We saw the same kind of development in 3D printing. The first machines were only used in service because they were too expensive and they required a lot of knowledge and know-how to use them in your own company. Do you expect that between now and a couple of years there come small CT scanners which people can buy themselves and use in their own manufacturing shops?
Well, I can well see that CT is a method that becomes more widely available, and also that CT scanners will be installed in more and more companies and more factories. From the complexity of things, I don't expect it to become much simpler because the physics is quite clear, and also in terms of radiation safety and so on. So I don't think that CT will be something that anyone can do at home.
Okay.
But yeah, there certainly will be an increase in the availability of the systems.
Okay. Then finalize. You wake up 10 years from now. How does your world in CT scan, do you think, look like in 10 years from now? What has happened?
Well, certainly higher resolution scans, faster scans. The topic where we're just starting is automation. So that, well, I guess at some point it will be more programming work in the beginning, and then push a button and then the samples will be processed. Whereas right now it's still lots of individual steps that one takes.
Okay. Good. I hope your wish comes true. So that is the end of your presentation.
Okay.
Thank you very much. And again, Thomas, and again, in our audience, a virtual applause from your side back home in your office is welcome. And we try to listen to this applause. It's for you, Thomas. Thank you very much.
You're welcome. It was a pleasure.
Okay. Then let's see, ladies and gentlemen, we're going to go to the next slide. You will find over there how you can, and now it's on the screen, how you can participate in a quiz. And for about 14 days, you can fill up this quiz. And as I said up front, you can win one scan, which Thomas will do for you about your business or your private model or material, whatever you wish. This is what's going to happen. And we see the results back, if they're not confidential, of course, maybe on the website, the results we will see. Thomas, thank you again for your presentation about this innovative technology. There's a lot of work to do, and a lot of people have to be aware of the fact that it exists and they can use it. And we hope to contribute by knowledge sharing that happened today between you and our audience. Thank you again. Thank you again for joining us, ladies and gentlemen. We hope to meet you on the next Knowledge Center Sharing event, a webinar on March, what I said this time,